Hello everyone, my name is Dariusz Sosnowski and today I wanted to talk to you about flexible parsing in Flow API, and this presentation was co-authored with Ronnie Marianai, also from NVIDIA. So in this presentation we'll basically be tackling similar problems as Shobi and Tim mentioned. So first I'm going to walk through specifically how packet matching is defined and how applications use Flow API to define packet matches on the hardware flooded rules. Then we'll talk a bit about custom protocol matching and what would be needed from Flow API to allow applications to add custom protocols in the Flow API. And afterwards we'll discuss the flex flow item, which is part of the Flow API, which aims to provide applications ability to define these custom protocols. At the end, we'll also talk a bit about requirements of packet patterns, flow patterns in the Flow API, and how we can maybe reduce them to allow a better architecture of the hardware offload. So first, a very brief intro to the Flow API after already 2 presentations on matching. So basically, in the Flow API, it gives DPDK users an ability to program custom behavior in the NIC so that the CPU is offloaded from some tasks. The basic concept in the Flow API is a flow rule, which consists of main 2 components. A pattern, which defines which packets we want to work on, and actions, which defines what to do with the packets, matching the given pattern. In DPDK, this API is available in both synchronous and asynchronous version. The asynchronous version is called the template API. So let's focus on the packet matching itself. So the main building block in the Flow API to build our description of the packets we want to work on is the RTFlow item. RTFlow item has a type, which basically defines whether this will be described Ethernet header, IPv4 header, IPv6 header, etc. It has a spec, which is a pointer to the header struct containing the values we want to match on, like the specific values, whether for example, the addresses or ports in layer 4. We have the mask, which defines which bits of the header we want to match on, so that basically the hardware will only look at those and the rest will be disregarded during the matching. And we also have a last, which defines basically the end range. If we wanted, for example, to match on a range of IP addresses, then spec and the last will define from which address to which address we'll match. And we can take a look at more complex examples. So when we have the RTFlow item itself, then the whole pattern is built as an array of flow items. In this example, we have an Ethernet, IPv4, UDP, and VXLAN pattern. So each item specifically defines through spec and mask the values we expect in this layer. For example, Ethernet item defines in the Ethernet header what kind of destination MAC address we want. IPv4 item defines the destination IPv4 address, and the VXLAN header can define the expected VNI value in the VXLAN header. As you can see in the Flow API, there is an expectation requirement that the pattern itself resembles the structure of the packet. So the items are ordered as it resembles the structure of the packet headers in the packet themselves. There is also some implicit assumptions. So for example, if IPv4 item follows an Ethernet item, then it means that the driver has to configure an implicit match on the ether type, so that we only match on the IPv4 packets. And the same happens for UDP, where we match next proto value in the IPv4 header. And for example, in VXLAN, this kind of implicitly forces the destination port to be implicitly matched to the specific value. But what if we wanted to support custom protocols matching? Different use cases might require either matching on protocols which are not yet added to Flow API, or match proprietary protocols which cannot be fully upstream or open sourced. In other systems, other APIs such as P4, where we'll go over the example, we can define our own parser from scratch. So in P4 language, there is no built-in definition of how even standard network headers look like, and developers define them from scratch. So for example, here we define our structure of the Ethernet header, in this case without any VLANs. And the parser is defined as a kind of a state machine. So we start from the start of the packet, we assume that all the packets are Ethernet, and we go to the parse Ethernet state. In this parse Ethernet state, we assume that whatever bits we got in the packet are Ethernet header, and we extract the value of ether type, and based on that we go to the next stage of the parser. In this example, we either go to IPv4 or IPv6 parsing stage based on the ether type value. If we, for example, go here to the IPv4 parsing stage, then as we all know, the IPv4 is a dynamic length header. The minimum length of the header is, I believe, 20 bytes, if I recall correctly, but we can have many IPv4 options. In P4, for example, we do not have to parse the whole packet header. We can only look at the parts we are interested in, and the rest skip. In this example, when we reach the parse IPv4 state, we extract the basic IPv4 header, and then based on the header length field in the IP header, we either go directly to the protocol dispatch state in this example, which based on the protocol value will continue, or go through an intermediate step, which will, based on the header length field in the IP header, will skip the unnecessary bits for us and will continue from there. So in this case, the question is, what kind of building blocks are needed in Flow API to achieve similar customizability as we have in P4? There are 4 main building blocks. So first, we need to know how to recognize the size of the new header. Our custom protocol can be either fixed size header, or the header size can be defined based on value stored in some field. This will allow our parser, this will allow Flow API and the driver to configure the NIC to know how many bits to skip when parsing this header. The second building block is we need to notify the hardware which bits of the header are really interesting to us, which bits we want to look at, which bits we want to match on, and which bits we want to modify. Let's say that for our custom IP, we only want to look at the addresses. The rest can be ignored, for example. The third building block is how to recognize what comes after our custom protocol. If we, for example, wanted to define a custom tunneling protocol, we need to know how to recognize what it follows. Basically, whether we encapsulate IPv4, IPv6, or raw layer 2 frames. And the last building block required is how to connect our new custom header to the existing ones. Let's say that we want to create a new layer 4 protocol. How do we recognize it in normal IPv4? It's important to note at this step that, as in P4, where everything was defined from scratch, it's not needed in Flow API that everything is defined using these building blocks. With these building blocks, the custom protocol could be attached to the existing hardware parser, so that we can only add a new protocol, connect it with IP, IPv4, IPv6, the standard versions, and connect them with other standard protocols, for example, for tunneling. And these building blocks are provided by the Flex Item API. This is available from DPDK 21.11. As of now, it's implemented only by MLX5 PMD. And basically, it exposes these building blocks so that now application users can create their own custom protocols and apply matches using these new Flex items, or even modify these custom headers through the Flex item. How the usage of this API goes on the high level. So first, we need to define a new item. There is a struct called rtflow flex item conf, which defines all these building blocks described previously. Then we register the new flex item in the driver. As part of this API, the driver configures the hardware, notifying it of reconfiguring the hardware parser so that it knows about this new custom header. And then we want to match or modify. We use either flex item type in the RTFlow item or field flex in the modify field action. So let's go step by step through the definition of the building blocks in this API. So first we need to define the header format and the header length. So it's critical for the hardware to know whether our new header is outer header, inner header, or a tunnel header. Or it can be both outer and inner. This information is required because depending on the type of custom header we want to introduce, a different number of hardware resources might be utilized. So for example, here I use the standard header as examples of how they could be defined in the Flex API. So for example, here we have UDP header, which is defined as mode multi, which means that it can be outer. It can be either outer or an inner header, or IPv4 header, which can be the same way. We also have VXLAN here, which obviously can be only a tunnel header here. But then knowing how this header can be must be interpreted on the stack of packet headers, now we need to know its length. And through the Flex API, we can define whether it's fixed, as for example with UDP and VXLAN, they are fixed length, and based on some field value. And Flex Item API provides an ability for the user to define the length of a header as some static value plus value of the field shifted by some bits. In case of IPv4, we use as the base header value 0, and we basically specify using bit offsets the location of the IHL field, the internet header length. We tell that it's 4 bits of size, and then we need to shift this value by 5, basically implementing the logic defined in the IPv4 header. Okay, so now we know what is our header used for, how long it is. Now we need to recognize, okay, when we parse it, how to jump from this custom header to next headers. For example, the encapsulated headers. This is defined through the next protocol field. There is one issue in the slides to be fixed later. But basically, we need to define where in the packet the hardware should look at to determine the subsequent header. So using the standard examples, so for UDP, there would be a field at 16-bit offset, taking 16 bits, it would be our destination port. This would allow us to decide what protocol follows UDP. For IPv4, we're basically using the same bit offsets and sizes, point to the next protocol field. Now, since through the API we'll tell the driver, okay, look at these bits in the custom header to determine the next parser, the next stage. Now we need to connect them to the existing parser stages in the hardware. This is achieved through configuring output links in the Flex Item API. And in this case, for example, this uses standard RTFlow item types to define what type of protocols will follow our custom header. And in this example, we specify that if, let's say, we define IPv4 header, then we can have that it can be either TCP if now our next header value is IP proto TCP, or it can be UDP if the value is IPv proto UDP. Now for the last building block, so now we have second to last building block. Now we need to take our custom header and connect it to existing parser stages in the hardware, so that the hardware knows that when we see specific, for example, UDP destination port or ether type or IP protocol value, we need to start parsing our custom header. This is defined through input links in the API, and basically each link is an RTFlow item using the predefined types in the API. In this example, for example, IPv4 or IPv6. And through spec and mask, we define the header values we need to match on. And from these values, the custom header parsing must start. And as a last step, we need to tell the driver through this API which fields are we really interested in looking at. This is called sampled fields. And we basically, in this API, provide a list of fields specified by bit offset and the bit size. In this example, if we define as custom TCP header, and let's say that we're only interested in the source port, destination port, and TCP flags, we provide 3 sampled fields, each with specific offsets and sizes of the fields we are interested in. These sampled fields will basically determine for API users which values we can match on and which values we can modify. And now if you want to match using this flex item, we basically use the standard RTFlow item struct with the type of flex and provide the handle to the already registered flex item. So after we configured the flex item using the building blocks, we register it in the driver, hardware is configured, we receive a handle. This handle is used in the spec and mask of the RTFlow items, and we provide in the API we provide an arbitrary byte array which defines which bits of the header we want to match on, which must resemble like the samples we provided as well. In this case, since we were using the standard protocols, we can reuse the TCP header struct defined in the DPDK API, but this can be any arbitrary byte array. And the similar thing is also for packet modification. So there is an action called modify field, which is a generic single flow action, which can be used to either modify a packet or a copy value from one packet header to another, or from between fields in the same header. And in here, when we use this action, we can also use as a destination or source, we can use the flex item with the provided flex handle. In order to copy a very specific part of our custom header, we specify the bit offset, the same as in the similar manner as in definition of the flex item. So now going a bit on the tangent. So okay, we have in the Flow API ability to add new custom protocols, and we can define basically the whole header structure in the Flow API. But what if we wanted to reduce them? Because as I mentioned, the Flow API requires a pattern, the array of RTFlow items, to represent the whole header stack. If I want to match on VXLAN packets and I want to look at both outer and inner header values, I need to define Ethernet, IPv4, UDP, VXLAN, then again, Ethernet, IPv4, UDP, and so on. This can cause several issues. For example, this makes the matching specification longer, which increases hardware resource usage. We might need more memory to store such rules. And it also requires more software computation. Basically, whenever I need to add a rule, I need to provide all the headers again and again. And also, in many cases, this is unneeded because, for example, I only care about inner headers. I don't care whether it's VXLAN or VXLAN in IPv4 or VXLAN in IPv6. I only care about the inner headers. I don't want to provide and I don't want to match on the outer headers themselves. It would be easier if it would be allowed on the API level that I can split the matching in phases. That in phase 1 I match the specific tunnel, which I allow, and the second phase I match on the inner header contents. This is allowed in relaxed matching. This is part of the Flow template API, so the asynchronous version. And basically, in the template API, I can provide the pattern template, which describes what I want to match on. And by specifying that this pattern template is relaxed, I lift the requirements as in normal Flow API. So there are no ordering there is no assumed ordering limitations, and most importantly, there are no implicit matching limitations. As I described previously, when I put IPv4 item after ETH, there is an assumed match on ether type. With relaxed matching, there is no such thing. And in this would allow basically the splitting in stages. So for example, now in some very small set of rules, I can match that, hey, I want VXLAN with IPv4 UDP protocols on the outer headers, or with IPv6, or even totally unrelated tunneling protocols such as GRE. I can match my required tunnel headers in the first stage, and then in the second stage, I can omit the outer headers and just match on the inner ones and the fields on which I only care about. In this example, VXLAN is used without any match. It's kind of an indicator to the driver that the items following that are inner, because RTFlow items themselves do not have any kind of way to specify that it's outer or inner. It all depends on the order. So this VXLAN is used as kind of a marker. This kind of design and this kind of relaxation of the requirements provides two main benefits. First, we can reduce the rules length on the rules which matter for us. We can imagine that these inner header matching rules are in a very high scale flow tables, like a few million flow rules. By reducing the rules length, we can fit more of them. We can lower the hardware resource usage and also improve the flow offload on the software side. We only need to provide the data we really need. We don't need all of the other items to, we do not need to fill other items to just fill in the requirements of the API. And it also enables table unification, which improves it simplifies the design a bit, because right now you can notice that it doesn't matter for me when matching inner headers whether the outer header was IPv4, IPv6, VXLAN or GRE. In this example, I only care that, hey, I want to match tunneled traffic. I don't care about the tunnel itself. So what I do is in the phase one, I match the accepted tunnels and then don't care about the specific tunnel at all. Which brings to one point, as you may have noticed, I used VXLAN as an indicator of that, hey, the following items will be inner headers. One improvement we can do in this whole approach is to introduce the generic tunnel item, which would not be used to match specifically all the possible tunnels supported by the hardware, but in relaxed matching would serve as an indicator of, hey, the subsequent items will be inner headers. But this is something for possibly discussion after the talk. Thank you very much.
Questions?
You mentioned that this is only supported in MLX5, right?
Right, yes.
Are you aware of any plans to support it in other PMDs or whatever?
I don't know of any plans. Yeah, it's basically a question to the whole community.
Yeah.
I would love that the Flex Item API or Relaxed Matching or even the template API itself, which is only supported MLX5, it would be great to see adoption of these APIs in other NICs. As we have seen, like there are capabilities to match custom protocols. It's up for discussion. Okay.
No more questions? Thank you.
Thank you.